Hello everybody, in this lecture we will be solving 1998 IMO problem number 1. Here is a view of this problem. When we check, we realize that there is an if and only if statement that needs to be proven in this problem. So as a result, I will first start with this direction, assuming that let A, B, C, D be a cyclic quad. And starting with this assumption, I would like to show that triangles ABP and CDP have equal areas. So let's go ahead and draw this cyclic quadrilateral. There you go. So we have our circle. So we are told that the diagonals AC and BD are perpendicular to each other. So let me go ahead and draw this picture. So probably we can make it such that so that would be AC, and BD, I don't want to make it look like 45 degrees, so let's just put it like here. So that would be B and D. So we have our cyclic quadrilateral. This is a 90-degree angle as stated in the problem, and we are told that AB and CD are not parallel, which is obviously the case here. And suppose that P, the point P, is where the perpendicular bisectors of AB and CD meet. So the perpendicular bisect, so AB is just a chord of our circle. As a result, the perpendicular bisector will go through the circumcenter of that of this circle, the center of this circle, I should say. Sorry for that. And similarly, the perpendicular bisector of DC as well will go through that point. So that point P is the circumcenter, and let me actually go ahead and also connect P to the four corners of our thing. So you have a perpendicular bisector here. For instance, this one is equal to that. In a similar way, let me quickly do it, I guess. And this is also 90 degrees, and this is simply equal to that. So, but it is obvious that P is the circumcenter of this shape, right? Okay, so now all we need to show is that the areas of these two triangles, ABP and CDP, being equal. Let's write down first the area of ABP, I guess. So using the area formula involving the sine function, so 1/2 AP times BP times sine of angle APB. In a similar way, one can easily find that the area of triangle CDP would simply be equal to 1/2 CP times DP times sine of angle CPD. But then notice that AP, P being the center of this circle, BP, CP, and DP, they are all equal to the radius R of this circle. So therefore, what we get is that this guy here is equal to R squared over 2 times sine angle APB, and this one is also R squared over 2 sine angle CPD. So therefore, all that remains is to show that these two angles, they are either equal, which is not necessarily the case. Nothing in the problem warrants that AB is necessarily equal to CD, or in fact, so therefore the problem is reduced to show that angle APB plus angle CPD is equal to 100. If we can show that, then by a well-known property of the sine function, the sine of these two angles would simply be equal to each other, and as a result, these two areas would come out equal. So, but why is that the case? Obviously, we have not made use of the fact that this is a 90-degree angle. The diagonals meet at a 90-degree angle. So let's try to make use of this fact. In fact, let's start with angle APB. Notice that angle APB is simply twice the angle ACB, and this is very easy to see because they both subtend arc AB, and second of all, let me actually go ahead and draw this line that I'm claiming. So this line here. So now obviously this angle here also subtends arc BC AB, except that it's on the circle, right? So as a result, it measures half of APB. In a similar way, angle CPD is equal to twice the angle CBD. And now if you simply focus on triangle, this point, the intersection of the diagonals, let's just call it as Q. So if you focus on triangle BQC, we observe that we just found out that two of the angles sorry for that, ACB, so ACB is one angle of this right triangle BQC, as is the other one, right? So this one here, and CBD is also another angle of this right triangle. So what I'm trying to say is that so because this triangle is a right triangle, this implies that angle CBD, which is the same thing as CQB, right? So angle CQB, CBQ, I should say, sorry for that. CBQ plus angle BCQ is equal to 90 degrees. But then this is the same thing as saying angle CBD plus angle BCD. Sorry for that. CBD plus angle ACB. Sorry for that. ACB is equal to 90 degrees. But if those two angles are 90 degrees, obviously APB plus the sum of angle APB plus the sum of angle CPD is just 2 times angle ACB plus angle CBD. But these two angles, they are adding up to 90 degrees, suggesting that these two angles add up to 90 degrees. So therefore, we simply showed what we needed. If those two angles add up to 180 degrees, as a result, their areas, because we have all these terms the same, the sine of these two angles would be the same. As a result, these areas are simply equal. Okay, so we are done with the first part. Now in the second part, we need to show that, so the other direction. All we need, actually, let's just write it like this. So for the second part, which is slightly harder, we need to show that if the areas of triangles, what were triangles? Let me see it again. ABP and CDP. So ABP is equal to CDP are equal, would imply that ABCD is a cyclic quad. Now just notice that if you call this statement as the hypothesis as P and the conclusion as Q, so we want to show that P implies Q. Alternatively, that would simply be equivalently, right? In logic, equivalently, this would be the same as proving this. So if I can prove not Q implies not P, then I'm done. So what I mean is that, so equivalently, I would like to show that if A, B, C, D, oh, this is a B, is not cyclic, I need to show this, right? So show that this would imply simply that area of triangle ABP would not be equal to area of triangle CDP. And that's exactly what I want to do next. Now let's start by simply drawing ABCD again. So I will need a bit more space here. So Because the diagonals AC and BD are perpendicular to each other, maybe I can start with drawing these diagonals. So consider this point as A, that's probably C, and yeah, so that's a 90-degree angles here. Sorry, that's a B, and finally, say this is D. So we have this non-cyclic quadrilateral here, and we are interested, like previously, let's call this point here as Q. Actually, let me make this a bit larger. Okay, and like previously, we need to find the perpendicular bisector of CD. The midpoint, let's assume, is somewhere here. So I draw a perpendicular line here. That's a 90-degree angle. And in a similar way, I draw a this line is pretty messy actually. Let me first fix this line into a better shape. Yeah, so something like, so after cleaning this mess, yep, yeah, like that. That's pretty decent, I think. Okay, so therefore, going back to our green color, so when we draw the perpendicular bisector, I don't know, so let's say something like this. So this doesn't look like 90 degrees, isn't it? So let's go backward. I don't need that. Okay, good. Okay, so the midpoint is somewhere here. Actually, no, it's probably somewhere closer to B. Yeah, somewhere here. So I draw a 90-degree angle. So shoot. Yeah. So yeah, let me just move it a little bit this side so that it doesn't hit this point here. So the midpoint of CD, so this was the midpoint of CD here. Let's call it as M, and that's my point P here. And this point we can call it as M. This is also the midpoint here. Okay. Well, obviously a couple of observations. Still, we have that AP is equal to BP. That's reasonable, right? And so let's go back to the original size. Yeah. So we still have that AP is equal to BP because P lies on the perpendicular bisector, and similarly CP is equal to dP because P also lies on the perpendicular bisector of CD. Yeah, so let's go back to big shape. So therefore this is equal to that. Okay, now at this point I will make this, well, obviously let's start by making this assumption without loss of generality. We can assume that AP is greater than CP, and what I will do is I will focus on the following circle. The circle centered at, so consider circle centered at P with a radius AP. That's the crux move here. So when I consider that circle, I claim both points C and D will lie inside that circle. So I will try to draw to the back, and that's obvious, right? AP is greater than CP and DP, so that's obvious. So we have this circle here, something like that, I would say. Now, what I will do next is I will, first of all, let's now go back to the big size. So I will extend AC, and I will call this point as C prime, and I will also extend BD, and I will call this intersection point as D prime. Now, and let me go ahead and, by the way, connect C prime and D prime as well. So I would like to make a couple of observations here. Actually, from now on, I will just make use of this picture. Notice that a few things. Yeah, so first of all, we know that QC or QC prime is greater than QC, and in a similar way QD prime is greater than QD. These two would imply that because we have right triangles, if you focus on right triangles CQD and C prime QD prime, this would imply that the hypotenuse C prime D prime is larger than the hypotenuse CD. But in a similar way, now I will make the following thing again. I will drop a perpendicular from point P to the chord C prime D prime. Okay, so I need to make it even larger. So if from this point I drop this perpendicular bisector, let's call this as N prime. So if I drop a 90-degree angle here, so it will bisect this, right? So like that. Or you can I think that's obvious, right? Because P is the center of the red circle, and any the point the segment that connects the center of this circle to the midpoint of any chord would be a 90-degree angle here. So what I'm trying to say is, notice that Pn obviously is strictly less than, if I make this picture even larger, so this point here, let's call it as x. So Pn, because you have the right triangle Pnx, so Pn is definitely less than Px, which is Pn is just the leg of the right triangle versus Px is a hypotenuse, but x is on segment Pn prime, so as a result this is less than Pn prime. But now combining these two results, this would imply that CD times Pn is strictly less than C prime D prime times Pn prime. Why? Because CD is strictly less than C prime D prime by the first result, and Pn is less than Pn prime by the second result. But all I can do now is, if I divide both sides of this expression by 2, I just realize that the left hand side is simply the area of isosceles triangle CPD, versus the right hand side is the area of isosceles triangle C prime PD prime. So therefore this implies that the area of CPD is strictly less than the area of C prime PD prime. But now go back to the the first part of our proof. We have consider cyclic quadrilateral, right? Cyclic quad A, B, C prime, D prime. Now, because it's a cyclic quadrilateral, and because the diagonals AC prime and BD prime are 90-degree angle, it must be the case that area APB, so this implies, by the first part, that area APB is equal to area C prime PD prime. But recall that C prime PD prime has greater area than CPD. Area CPD. But then that's the desired result, right? So recall early on our let's go back to the 100%. Yeah, so our whole goal was to show that if ABCD is not a cyclic quadrilateral, ABP and CDP have different areas, and ABP here have different area than CDP. So we proved it as claimed, and that solves this beautiful problem. Hope you enjoyed this solution, and looking forward to see you guys in our next video.